In this video, we will focus a little bit on the acids, because one of the things that we're going to be discussing in the whole chapter is strength of acids and bases. And well, we want to know what makes an acid stronger, what makes an acid weaker, and the same thing goes for bases. But when we talk about acids, it's a little easier to understand what makes an acid stronger or weaker. So that is the purpose of this video. We're gonna take a look at the structure, the molecular structure of some acids, and then try to understand what makes this particular acid stronger than other. So the acids can be pretty much of three types. We have the binary acids. Those are kind of the common and also referred to as mineral acids. The oxoacids are also very common. And within the oxoacids, we can refer to the organic acids, but we consider the organic acids like a whole family on its own. So we're going to have pretty much the binary acids, the oxoacids, and we are going to limit our discussion here probably just to the binary and the oxoacids. So when we look at binary acids, by definition, a binary acid is it contains hydrogen and a non-metal, whatever they are. The common binary acids that we have to deal with are in this table. And this table is telling you pretty much also in what order that strength increases. Okay. Here we are looking at pretty much a position according to periodic table. Let's forget about this because this is group 17 and this is group 16. Okay, so we are looking at going in that direction in the periodic table and in that direction, and those directions are telling you if you move in that direction, then you are making the acid stronger. Okay, so we are looking at polarization, and polarization depends on electronegativity of the elements that are at hand here, and particularly for the hydrogen, because we are looking here hydrogen plus something else. Well, the electronegativity of hydrogen will be the same no matter what, but then the reaction, the polarity of that bond will depend on the nonmetal and the electronegativity of that nonmetal. And remember, electronegativity is that tendency of attracting a pair of electrons that are part of a bond in which that atom is participating. So here we are looking at number one, we are looking at a more polarized bond. Okay, and a more polarized bond means, okay, there is a larger electronegativity difference between the metal, the non-metal, and the hydrogen. So if you compare water, let's do it this way. If you compare water and HF, in this case let's call it hydrofluoric acid. Well, fluorine has a larger electronegativity than water. Therefore, the bond on hydrofluoric acid is going to be more polarized than the bond on water, and therefore hydrofluoric acid is going to be a stronger acid than water. So that happens with that happens when you move across periods. So across periods, electronegativity increases, therefore bond polarity increases. Okay, and acidity increases. Okay, now if you are moving down a group, then the acids will become stronger. And the reason for that is, well, yes, polarization has to do something with acidity. It will make the acid stronger. but also it might make that bond stronger, because polarization means those partial charges are also stronger. So the more polarized a bond is, the stronger those partial charges are, and the more strongly they attract each other. Okay, so for example, if you have HF, has a partial positive charge and a partial negative charge here, and you're comparing this with that, then the strength of how big those positive charges, those partial charges here, are stronger than the charges that you see here because of the difference in electronegativity. That means that the bond in HI is actually weaker than in HF. What does that really mean? What does that matter? Okay, remember, this is an acid, correct? The acid must release the H plus. To be considered an acid, the acid must release the H plus. If it doesn't, then it won't be an acid. Okay, so the easier that acid releases the H plus, the stronger the acid is. So fluorine is very electronegative, correct, compared to iodine. So because fluorine is very electronegative, then those partial charges will be very strong, and then there is going to be a stronger attraction between the H plus and the fluoride. So in that case, in that compound in hydrofluoric acid, that fluorine is not very willing to let that proton go. He wants to have it close by. However, for hydroiodic acid, which is this one, well, iodine is not that strong. It's still an acid, but because iodine is not that strong in terms of electronegativity, those partial charges are not so strong, so the attraction between the proton and the iodide is not as strong as in the case of hydrofluoric acid. So that proton from hydroiodic acid is really ready to go. It will go a lot easier than in the case of hydrofluoric acid. Okay, so that's the main thing here. So if you move down a group, okay, it doesn't have to be halogens, it could be anything in the periodic table for non-metals, will have the same behavior. Down a group, and let's put this, electronegativity decreases. Okay, you can say bond strength decreases as well. Okay, because that attraction between the H plus and the corresponding anion is not as strong, but because of that, the acidity goes up. Okay, so if you are in the same period and you're comparing bond polarities, the more polarized bond will give you a stronger acid, but if you are going down a group, that bond actually becomes weaker and weaker and weaker, but making a bond weaker, an a hydrogen non-metal bond weaker, means you are making it a stronger acid. Okay, so do not think that you need a strong bond to be a strong acid. You actually need a very weak bond to make a strong acid, and the reason for that is because a strong acid will release the proton very, very easily. Okay, and therefore, if to be able to release it very quickly, then that bond has to be weak as well. Now, in the case of oxyacids, it's a little bit different story. I mean, we can still use electronegativity and all of that to explain strength of acids, but the way you interpret these, the rules, the electronegativity, for example, goes kind of in the opposite direction. And what I mean by that, let's take a look first at the structure of those acids. In the binary acids, proton is attached to nonmetal. In the oxyacids, the proton is always attached to oxygen. Okay? Oxyacids, a proton attached to oxygen. And that makes things a little bit different, because now if we are looking at the acids, in a binary acid, what you have is HX, right? Simplify. You want this bond weak to make an acid stronger. In an oxyacid, if we take this, now you have HOY. It is this bond, the hydrogen oxygen bond, the one that you want to be weak. Okay, so the nonmetal has a larger impact here in terms of the strength of that hydrogen nonmetal bond, but here the impact is a little bit different, because it's not affecting the bond directly, it's affecting the oxygen, and in consequence it will affect the bond. But let's take a look at what I mean for that matter. Okay, so the more electronegative the Y atom is, the stronger the acid is. If we take a look, for example, if we are comparing HCl versus HI, HI is stronger, right? But here we are seeing the opposite. Now, why is that? Well, in this case, iodine is less electronegative, right? Because it's less electronegative, here in this case, the bond between the hydrogen and the iodine is weaker. But now what we are comparing is this versus this. Now, because chlorine is more electronegative, then it's, remember, the electronegativity means the atom is pulling electrons toward itself, right? So there is, because chlorine is more electronegative, then is pulling more electrons from oxygen than what iodine can do. Because chlorine is better at pulling electrons from oxygen than iodine, then the oxygen in HOCl is weaker. Think in terms of the oxygen here having a stronger partial positive charge because of chlorine than what you see here. Okay, therefore the hydrogen oxygen bond in this case is weaker, and it makes it a stronger acid. Now, when you have larger oxidation numbers in the central atom, the acid is stronger. Okay, so here particularly, carbon will technically have a +4 and boron will have a +3. Okay, and not necessarily something that you will that is easy to picture, okay, in terms of electronegativity. But carbon is going to be more electronegative than boron, so to speak. Therefore, you will see that this acid is stronger. Okay, so now the number of oxygens that you have here also plays a role, because you have let's use this one. Okay, so why are these acids different in strength? So remember, the chlorine is trying to pull electrons from the oxygen, okay, and in doing so makes that bond weak, correct? So now what happens if you start putting more oxygens around that central atom, around that chlorine? Well, those extra oxygens there are actually helping chlorine do a better job, because here these oxygens will be pulling electron density toward themselves, and in doing so, then this chlorine would be better able to pull electrons from that oxygen attached to the hydrogen, and in this case with 3, well, even more so. So those extra oxygens around the central atom there, around the chlorine, are actually helping chlorine to draw electron density from the oxygen, affecting the hydrogen-oxygen bond, and making it weaker. So this is going to be weaker, and this is going to be the weakest. Okay, so and the take-home message here is that a weaker HO bond, the stronger the acid. Okay, that's what you are aiming for. Whatever affects that hydrogen non-metal, and in this case hydrogen-oxygen bond, will make the acid stronger. In this case, increasing the number of oxygens will help that central atom, that chlorine, to drain that oxygen from electrons, and therefore weakening the hydrogen-oxygen bond. If we want to give numbers to this, and remember this is Ka, that is the acidity constant, and of course it's going to be a measure of how strong the acid is. What we are looking at here is, for example, if you have let's say HOY plus H2O, this is an equilibrium reaction, and what we are looking at is OY minus plus H3O plus. That is your equilibrium reaction. And since we have already worked with equilibrium constant, well, that's this Ka describe that equilibrium. The larger the value of Ka, of course, it means that reaction is favoring products, and therefore if you are favoring the process of transferring that electron from the acid to water, you are making the acid stronger. So the acidity constant is a measure of acid strength, if a numerical value, so to speak, for acid strength. And what you're looking here is difference in electronegativities For oxyacid, and this is very important, for oxyacids, if the electronegativity of the central atom increases, Ka increases. And if Ka is a measure of strength of an acid, then strength increases. Now remember, if sometimes, particularly for equilibrium reactions, and let's talk about a generic acid. Technically, it's more correct to say Ha plus H2O goes to H3O plus A minus. But you can use that reaction, or you can just simply say Ha goes to H plus A minus, and those are perfectly equivalent. Okay, so what is happening to the acid in aqueous solution? The acid is splitting in two, is dividing into ions, pretty much like an ionic substance. Okay, so because you are dissociating that acid and you're producing ions, then acids are also electrolytes. Okay, acids and bases are electrolytes, and they are electrolytes because they generate ions in solution. Okay, but with the concept of strong and weak electrolytes also applies to acids and bases. So a strong acid will be considered a strong electrolyte because when you put a strong acid in water, will pretty much completely dissociate, completely separate into ions. And a weak acid will only partially ionize. Okay, so let's highlight important stuff here. So a strong acid is a strong electrolyte because there is pretty much complete ionization of the molecule in water. Okay, and a weak acid is a weak electrolyte because there is only partial ionization of the molecule. Okay, strong acid, complete ionization; weak acid, partial ionization. And when it comes to strong and weak bases, the analysis is pretty much the same. Okay, so strong base, strong electrolyte, complete ionization. And weak base, weak electrolyte is partial ionization. Okay, it doesn't matter if it's an acid or if it's a base. They can be strong or they can be weak. Strong electrolyte implies complete ionization. Weak electrolyte implies partial ionization. So we are just extending the concept of electrolytes, the concept of strong and weak electrolytes, to acids and bases. And that has an impact because later on, when we start doing calculations, it will matter whether you are working with a strong acid or a weak acid, or strong, weak base for that matter. So it's the analysis is very, very similar, but you need to know whether it's a strong acid or a weak acid. One more thing to do to understand here, we are looking at acids and we are trying to compare how the strength of acids just by looking at similar acids, right? So we have already said that higher oxidation number, particularly in the case of oxyacids, will make the acid stronger. So here, for example, we have sulfur is +6, but sulfur is +4 here. So higher oxidation number stronger acid, so sulfuric acid is stronger than sulfurous acid. In the next case, we have nitric acid versus nitrous acid. So here in nitrogen is +5, and in nitrous acid, nitrogen is +3. Okay, so those are easy to picture, but this one is a little more interesting. Okay, because we are comparing, in particular, let's take a look here at water, right? We have already said that water can behave as an acid or can behave as a base, right? So if it behaves as a base behavior, it will accept a proton and it will become H3O plus, right? And if it behaves as an acid, then it will donate, it will release a proton and it will become H minus. Okay, so now you have, this is a conjugate pair, this is a conjugate pair, H3 plus OH minus is not a conjugate pair. Why not? Well, H3O plus have 3 hydrogens, OH minus have 1 hydrogen, the difference is 2 hydrogens. Even if they are related to another substance and they are part of a conjugate pair for that other substance, between them, those two species are not a conjugate pair because you cannot obtain one from the other in a single proton transfer. Okay? So, in order for a conjugate pair to be a conjugate pair, the difference is only 1 proton because you can obtain one from the other with a single proton transfer. So that's the main thing here. But if you're comparing acidity here, the more hydrogens you have in that structure, the more acidic it will become. So if you're looking at these 3 substances behaving as an acid, H3O plus, H2O, and OH minus, if you want to look at them from the point of view of an acid, this is going to be the strongest. We can this is going to be stronger and this is going to be weaker. Okay, if you are comparing those 3, and the same thing applies to any other substance in which you can obtain multiple structures by changing the number of protons. Okay, so the higher number of hydrogens on a structure will give them a stronger acid character. So that's the main thing here. Okay, so